Okay, thank you for your kind introduction and welcome to my talk. So, as depicted here, we consider notched anisotropic composite plates, and we are interested in the asymptotic near-tip field here within the framework of the first order shear deformation plate theory. So, I start with a short motivation and an introduction of the governing basic equations. Then I will describe the applied asymptotic complex potential approach and finally present some results and conclusion. So within the framework of linear elasticity, stress singularities may occur in different situations, for example at geometrical discontinuities, such as corners or sharp notches as depicted here. And due to these high stress concentrations, the initiation of failure or the track initiation can be expected right there, and therefore a detailed structural analysis is necessary. Due to these high localized stresses here, the classical Kirchhoff-Lens plate theory is unable to render correctly the asymptotic near-tip field, which is basically due to the kinematic assumption, and that's why higher order plate theories are required. So, the present study focused on the asymptotic near field, which means the field variable stresses and displacements in the vicinity of the notch tip, in the vicinity of the singularity, which is of particular interest in fracture mechanics. And here, methods of asymptotic analysis can be applied very advantageously. From this near-tip field, from this asymptotic field, the singularity exponent lambda as a measure of the strength of the singularity can be deduced directly. Furthermore, the asymptotic near-tip fields allow for combination with numerical methods, and especially here for a very efficient calculation of the generalized stress intensity factors, which are necessary in fracture mechanics analysis. In the present work, the complex potential approach is applied, which has the advantage that even if the singularity exponent is complex, the physical requirement of real-valued field variables is fulfilled automatically, in contrast to other approaches. And of course, the complex potential approach is a powerful method for the treatment of anisotropic material behavior. So let's start with the basic equations of the first order shear deformation plate theory. So in this theory, normals to the midplane remain straight, but not necessarily perpendicular to the mid-surface. The displacements can be written here in this form with inclination angles psi x and psi y. This displacement field, in combination with the stress-strain relations and the equilibrium conditions, leads to a system of coupled partial differential equation, which can be written here in this form. And obviously, closed form elliptical solutions to this coupled PDE system are hardly available, but asymptotic solutions can be obtained as described in the following. So, based on the very general theory of elliptic boundary value problems near conical points, the solution in the vicinity of the notch tip can be extended in this form here, where the first term here represents the leading order term approaching the notch tip. Here on the right-hand side, the singularity exponent lambda and associated stress intensity. So now, substituting this expansion into the PDE system and collecting terms of equal order in R, a reduced or a modified PDE system can be obtained. And the key point is now here, only second order derivatives appears in this coupled PDE system, and that's why a complex potential formalism can be applied to solve this system. So, without going into detail of the derivation, the general solution can be written in such a form potentials. So the derivation is basically was based on Leibnizian formalism, and these three polymorphic complex potentials depends on so-called generalized complex coordinates, with these mu's here are the roots of these two characteristic equations. It has to be mentioned here that this formalism degenerates for isotropic material behavior, but considering a small artificial anisotropy, also the isotropic case can be approximated very, very good. So the complex potentials are assumed to be of this form here, where this two-term approach is necessary in order to allow for complex singularity exponent lambda. Then, using this ansatz for the complex potentials, finally the bending moments and the transverse shear forces are of this order here, and in contrast, so these are of the same order, bending moments and the transverse shear forces, in contrast to the classical Kirchhoff plate theory. So from these relations here, it can be seen that singularities arise for the real part of lambda smaller than 1. Up to now, the singularity exponent lambda and the complex coefficient are still unknown. So the requirement that homogeneous boundary conditions along the notch faces are fulfilled leads to a homogeneous system of 6 linear equations. And yeah, non-trivial solution for exists only if the coefficient matrix here is singular. So finally, the singularity exponents can be deduced from this characteristic equation here, which is a nonlinear transcendental equation, so it is solved geometrically. Then, due to the linearity of the problem here, the solutions can be superposed. So finally, a complex potential consisting of different deformation modes is obtained. Okay, now I would like to present some results, starting with a comparison between the asymptotic solution and numerical data. So we consider a notch plate under symmetric loading, and we performed finite element analysis using abacus with conventional thick shell elements. So on the left-hand side here, the bending moments are evaluated along a circular path close to the notch tip for a 0-degree fiber direction. So just one fibrine composite layer. And it can be seen that there's an excellent agreement between the asymptotic solution and the numerical data for the 0-degree fiber direction and the 90-degree fiber direction. Let's continue with some results for the singularity exponent lambda, and here discuss the effect of boundary conditions along the notch faces, fiber orientation, and the notch opening angle. So let's consider the case of a notch with stress-free cracked faces. And in the figure on the left-hand side, the singularity exponent lambda, or the real part of the singularity exponent, is shown as a function of the angle gamma for 0-degree fiber direction, and here gamma is the angle between the x-axis and the notch face. So it can be seen here, first of all, that within the first order shear deformation theory, it can be distinguished between singularities for the bending moments, here as solid lines, and singularities for the transverse shear forces, here as the dashed lines. So these singularities are distinct also in contrast to the classical Kirchhoff theory. Furthermore, it can be distinguished between singularities associated with a symmetric loading and singularities associated with an antisymmetric loading here. So it can be seen that transverse shear force singularities occur only for an antisymmetric loading, and then symmetric loading leads to stronger singularities for the bending moment. So that's why this case can be load case can be understood as a critical load case. On the right-hand side, the singularity exponent is depicted for a 90-degree fiber direction, And here it can be seen that the singularities are stronger compared to the 0-degree phi direction. And furthermore, here the range of gamma leading to singularities for an antisymmetric deformation has increased. So there is, of course, a strong influence of the anisotropy on the singularity experience. Now let's consider a notch with simply supported boundary conditions. And yeah, starting here with a 0-degree phi direction, changing to 90-degree phi direction, two effects can be observed here. So first, the singularities associated with the symmetric deformation here are getting weaker, and the singularities associated with an antisymmetric deformation are getting stronger. So these two effects are present here. Furthermore, it's kind of surprising that there are very strong singularities for a nearly straight edge here, so it's kind of unexpected. And also, singularities are present over a wide range of notch opening angles, as can be seen here. Furthermore, what is also kind of surprising is that the special case of a 90-degree region in the corner, which is right here, has a singularity which is stronger than the classical refractive singularity here. That's also kind of surprising, but very interesting result. So let's summarize the main aspects of my talk. So we consider notch composite plates using first order shear deformation plate theory, and here we apply a complex potential formalism within an asymptotic analysis to obtain the asymptotic near-tip fields. Furthermore, we compared the asymptotic solutions with finite element data, and there is an excellent agreement for the phi directions. Furthermore, it has been observed that the singularity exponent is, of course, affected by the phi directions. And now this nearly closed form analytical solution for the near-tip field can be used in numerical applications, and especially here for very efficient calculations of the stress intensity factors where you have to know the asymptotic near-tip field. So thank you for your attention.